All right, so this will be the last lecture that I'm going to post on calculation of flexural displacements. Basically what I'm going to do here is go over some examples on how to identify boundary and continuity conditions. So if you remember the last example that we went through with the point load in the middle of the simply supported beam, we had to identify four boundary conditions or continuity conditions, right? Because we had to define two moment diagrams because there was a discontinuity, and when we integrated each one, we got two sets of integration constants for each moment diagram, so that became four integration constants, and so we needed these four boundary conditions to solve for them, right? So here, instead of going through and solving, really the difficult part of or I should say the new part that's difficult for these types of problems is to identify the boundary and continuity conditions, right? Because there's basically three steps here, right? Step one, maybe I'll do this right here. So step one, we want to draw and calculate the moment diagrams, right? Step two, we've got to integrate the moment diagrams twice, right? And step three is we've got to identify boundary and continuity conditions and solve for integration constants. Like that. And so the first one, and we've already done, right? We even, discussed that quite a bit on the midterm exam. And the integrating of the moment diagrams twice, well, that's just, back to calculus. And so really the new thing is the third step, which is to make sure that we're properly identifying the boundary and the continuity conditions so that we can solve for these constants properly. So I'm going to do two examples here. I'm going to give you the structure, and all we're going to do is identify, okay, these are the discontinuities, so we're going to need, four moment diagrams or four segments that we have moment diagrams for. That means we're going to need 8 constants of integration, and then I'm going to show you what the boundary conditions are that will allow you to solve for those 8 constants of integration, right? Okay, so let's get going. So the first problem that I wanted to do looks something like this, and we had a roller support there, and we had, let's see, 1, 2, 3, 4. So we have a uniformly distributed load here, right? And that is a fixed support, and each one of these dimensions here is L over 2. Right, like that. So I'm going to call these A, B, C, and D, right? And we are going to take X, we're going to take X from that side, right? And so in this case, we're always going to use the same X just for consistency here, but as you're actually solving a problem like this, you can use whatever coordinate system you want. I would just strongly suggest that they all go positive from left to right. Okay, so then what I'm going to do is I'm going to color this first segment here gray, right? And second segment here will be green, right? And the third segment, I guess I'll color red, just to distinguish it from the distributed load, right? So we've got these three segments, right? And we know that because the discontinuities are beginning and end of, at the supports, beginning and end of distributed loads, right? Those are the ones that we have here, that these three segments are each going to have their own moment diagram, right? There is not going to be a single moment diagram that's going to be valid across this entire structure, right? We'll have one from 0 to L over 2, one from L over 2 to L, and one from L to 3L over 2, right? Okay, so we need, if we've got three moment diagrams, right? So I'm going to say that we've got, I'll call this moment diagram, this is moment diagram 1 of X. This one will be here, which will be moment diagram 2 of X. And then over here we will have moment diagram 3 of X, right? And if we've got three moment diagrams and we integrate each one twice, right, that we're going to have 6 constants of integration. Which means that we are going to need 6 boundary and continuity conditions. Right? So let's go ahead and identify what these 6 boundary and continuity conditions are, right? So sorry. So I just realized I had, before I get too far, let me correct that. So this is actually supposed to be a pin support. It doesn't really change much if it's fixed. The thing that happens is it becomes a statically indeterminate problem, and so you can't really solve for the moment diagram. So so in this way, everything else is the same, right? So we still have the 3 moment diagrams. We still have these 6 constants of integration, right? And so what we're going to do is, I'm going to again try to do this in gray and red and green, right? And so here, let me draw these lines, which are just going to identify these sort of locations, right, where the boundary conditions might be defined. And the first one we're going to have is that V of 0 is 0, right? So at that pin support, there cannot be any movement, right? Then we're also going to have at point B that V of L over 2, right, for the gray elastic curve has to equal V of L over 2 for the green elastic curve, right? Basically, that the deformed shape requires that the elastic curve in the gray and the green have exactly the same value at B, because they're both defined there. Right? And then we can also write that dV dx evaluated at x equals L over 2 has to equal dV dx of the green curve evaluated at x equals L over 2, right? And you should start to notice a lot of similarities between these boundary conditions and the ones that we've seen in the last example, right? These both are what I referred to as relative boundary conditions, right? So I'm not telling you what the actual displacement is. I'm just telling you that both elastic curves have the same displacement, right? And I'm not telling you what the actual rotation is. I'm just telling you that both of these elastic curves have the same rotation. Okay, and then if we keep moving over here, so now we're at point C, Right, at point C, I know that the displacement is 0, so I can say that the displacement of the green elastic curve has to be 0 there. Right? I can also say that the displacement of the red elastic curve has to be 0 there. Right? So they are in fact the same, right? But because there's a support there, not only do I know they're the same, I know exactly what they are, right? And that's fundamentally the difference between a boundary condition and a continuity condition. So a boundary condition, I use them not interchangeably, but I always sort of group them together. So a boundary condition is something like V of 0 equals 0, V at L equals 0, V at L equals 0, right? I'm telling you precisely what the displacement or the slope is at a point. Then the continuity condition, what I'm doing is I'm telling you how these two elastic curves connect together, right? And so then the final one, right, so these are 5, so the final one here will be dv dx evaluated at x equals L. That has to equal dv dx of the red curve evaluated at x equals L. Right? So these are the 6 boundary conditions, right? That's 1, 2, 3, 4, 5, and 6, right? So obviously this would take a long time to solve, right? I probably wouldn't ask you to do something like this on an exam unless it was a take-home. But you could do it. And what I'm doing here is actually a really good exam problem because it shouldn't take too long, right? But I'm examining sort of the essence of, do you understand how these elastic curves kind of get hooked together, so to speak, right? Okay, so that is the first example. So let me move on to the second example here, right? So let me do this again. We'll do this in blue. So this one looks somewhat similar, like that. So now this becomes a hinge, right? That is a fixed support. 1, 2, 3, 4. This is a roller. 1, 2, 3, 4. It looks like that. And I have a point load that's down here. So that's P. And then I also have a distributed load here. Right. So somewhat similar, still statically determinate, right? I did change the left-hand support from a pin to a fixed, but then I added a roll or a moment release in the middle, right? So this is W, and then how did I do it? Did I do it in red? I did. So let me just rewrite that. So that's A. So then this becomes A, B, C, and D, right? So again, all of these A, B, C, D, these are the discontinuities. They're either at the supports, at a beginning or end of a distributed load, under a point load, you know, at a release, et cetera, right? And so the dimensions here, and we'll do them just the same, just for sort of consistency, so they're all L over 2. Right? And now I am going to highlight, again, using different colors, these segments. So that's segment 1. We highlighted that guy in gray. That's segment 2, highlighted in green. And then this guy is segment 3, highlighted in red, right? And so just like the previous example, I am going to get one moment diagram for segment AB. I am going to get a second moment diagram for segment BC, and I'm going to get a third moment diagram for segment CD, right? And again, I will take my x from the left-hand side, right? So again, 3 moment diagrams, I get 2 constants of integration for each one, right? So again, I have 6 boundary or continuity conditions that I need to identify because I'm going to have 6 constants of integration, right? So let me here extend these down just like we did last time. Okay. And now you'll see the boundary conditions that we're going to define aren't all the same, but there'll still be 6 of them, and there are only 6 of them, right? So the first one that we can do, if we start at the left-hand side, so point A, right, I can say that V of 0 is 0, so there can be no displacement at point A, right? But because it's a fixed support, I can also say that the slope at point A has to equal 0, right? So you can see that that is true, right? So slope and displacement are both 0 at point A. Let me just rewrite this a little bit so it's not so sloppy. Okay, so then at point B, right, now I don't really know anything about this. It's a continuity condition. Again, there's no external support there. It's a moment release, so I cannot say that the deformed shapes have the same slope because they may not, because I'm releasing the moment there, so there can be sort of a kink in the deformed shape. But what I can say is that the V at L over 2 has to equal the green V at L over 2. All right, so those 2 things have to have the same displacement. That hinge, that moment release, is not enforcing the same slope there, but it certainly is enforcing the same displacement there, right? So that's 3 boundary conditions, right, that we have, right? And then we need 3 more, right? So those are going to come from point C, right? And so similar to last time, I can say that V of L is 0, right? So the green elastic curve has to have 0 deformation at point C, right? I can also say that the red elastic curve has to have 0 deformation there. Again, that is a boundary condition. I have a reaction there, so I know precisely what the vertical displacement is, right? If I'm restraining the motion there, I am going to pick up a vertical reaction, so I know what the vertical deformation is. If you notice, there is no moment reaction there, and because of that, I actually don't know what the rotation is at that point. I can only say something relative about the rotation because, again, that is now a continuity condition, not a boundary condition. So this now I can say that dv dx at x equals L has to equal dv dx at x equals L, like that, right? And so now if I was going to number these, right, so 1, 2, 3, 4, 5, and 6, right? You always get precisely the number of boundary and continuity conditions that you need. There are no extra ones, right? So it's not like there's 6 others and I'm just choosing these particular 6. These are the only things, the only 6 that we have, right? So again, if I know something about the reaction, or if I have reactions, like if you look at A, right, let me just draw them here to sort of make this point, right? I have a vertical reaction there. I have a horizontal reaction. Actually, let me get rid of the horizontal one since we're not really dealing with the horizontal direction here. And I have a moment reaction there, right? Just drawn positive right-hand rule, positive up. Because I have both of those reactions, right, I know that the displacements associated with them, vertical translation and rotation, have to be 0, right? Because I don't know what the reactions are, but I know that their corresponding displacements are 0. right? And if you look at point C, right, again, if I look at point C, I have a reaction at point C, right? It is a vertical reaction. So now I know that the vertical displacements at point C have to be 0. So there's this sort of yin and yang type thing. If I have reactions, I know they're restraining the displacement. I know what the displacements are. In the case of point D, for example, there are no reactions there. So I can't say anything about the displacements. And notice there's no boundary or continuity conditions that are going to be written about a free end. Right? Okay. So with that, I'm gonna end this lesson. I'll upload it, and we can chat tomorrow at the office hours or on